Let me prove that whether the left side is equal to the right side in a Stoke's theorem. And I will take the same previous example. Verify Stoke's theorem if vector f equals to x squared plus y squared into I minus 2x times yj, which is a rectangular area located in xy plane from x equals to minus a to x equals to plus a and y equals to 0 to y equals to b. Solution. The formula of the Stoke's theorem is line integral equals to the surface integral. Stoke's theorem says that line integral always equals to the surface integral, which means that the left side equals to the right side. Let me draw the diagram. Here is my xy plane and the limits start from 0 to plus a. So I'm going to extend the x-axis to the left side to have minus x and similarly y to minus y. Let me draw the triangle. This is my triangular area which is located in xy plane. Name this point A with the coordinates minus a comma 0 and name this B with the coordinates a comma 0. Name this C with the coordinates a comma b. Name this D with the coordinates minus a comma b. This is my rectangular area which lies in xy plane. Along x-axis it ranges from minus a to plus a, where along y-axis it ranges from 0 to b. Stoke's theorem says that left side equals to the right side. So I'm going to first find the left side, the integral part, where C stands for the curve. For the curve of a rectangular or sides of a rectangular or border of a rectangular. Since the rectangular has 4 sides, and therefore I'm going to make C1, C2, C3 and C4. Name this side C1 where y equals to 0. Take derivative on both sides to have dy equals to 0. Name this side C2 where x equals to a. Take derivative on both sides to have dx equals to 0. Name this side C3 where y equals to b. Take derivative on both sides to have dy equals to 0. Name this side C4 where x equals to minus a. Take derivative on both sides to have dx equals to 0. You already know that line integration takes place in anti-clockwise direction. So let me start from C1, first C1 and then C2 and then C3 and then C4. It goes in anti-clockwise direction. Limits along C1 are x equals to minus a to x equals to a. Limits along C2 are y equals to 0 to y equals to b. Limits along C3 are x equals to a to x equals to minus a. Limits along C4 are y equals to b to y equals to 0. Let me first find the dot product of vector f and dr, where f is here, which is x squared plus y squared into I minus 2x times yj, where dr equals to dxi plus dyj plus dzk. Take derivative between these two terms where I times I equals to 1. Take derivative between these two terms where j times j equals to 1. Since the rectangular is in xy plane and therefore I don't have z, just put 0 here for the z. And this is my final value for dot product of vector f dr, which is x squared plus y squared dx minus 2x times y dy. Now I'm going to calculate for each and every side of this rectangular. Take C1 first, where y equals to 0 and dy equals to 0. Just substitute the value of y equals to 0 and dy equals to 0 in this equation to have x squared dx. The limits along C1s are x equals to minus a to x equals to a. Take integration on both sides, where the integration of vector f dot product dr is actually the integration along C1, and take integration of x squared dx with the limits x equals to minus a to x equals to a. So there is a minor mistake. The range starts from minus a to a, not from a to minus a. Integration of x squared with respect to x is x cubed over 3. Put the value of the limits, so finally I got 2a cubed over 3. Just put 2a cubed over 3 under C1 here. Now take C2, where x equals to a and dx equals to 0. Substitute the value of x equals to a and dx equals to 0 in this equation to finally have minus 2ay dy. Limits along C2 are y equals to 0 to y equals to b. Take integration on both sides, where the integration of vector f dr here is the integration of C2. And take integration of this term with the limit start from 0 to b. Integration of 2ay with respect to y is 2ay squared over 2. Put the value of the limits to finally have minus a times b squared. This is the final value for C2. Just put minus a times b square under C2 here. Just put it here. Now take C3 where y equals to b and dy equals to 0. Just substitute the value of y equals to b and dy equals to 0 in this equation to have x squared plus b squared with dx. Limits along C3 are x equals to a to x equals to minus a. Take integration on both sides. Integration of the left side is actually the integration of C3. And integration on right sides with the limits ranges from a to minus a. Take integration of x squared plus b squared to have x cubed over 3 plus b squared x. Put the values of the limits to finally have minus 2a cubed over 3 minus 2ab squared. This is the final value for C3. Just put this value under C3 here. Now take C4 where x equals to minus a and dx equals to 0. Just substitute the value of x equals to minus a and dx equals to 0 in this equation to have 2ay dy. Limits along C4 are y equals to b to y equals to 0. Take integration on both sides. Integration of the left side is actually the integration of C4, and integration of the right side with the limits from b to 0. Take integration on the right side to have 2ay squared over 2. Put the limits values to have minus a times b squared. This is the final value for C4. Just put C4 here under this integration term. Takes their addition, so finally I got minus 4a times b squared. This is the final value. Now I'm going to calculate for the right side, which is the surface integration. Let me first find the curl f, where vector f equals to x squared plus y squared into I minus 2x times yj. Curl f is actually the cross product of del and vector f, which equals to ijk partial or partial x partial or partial y partial or partial z x squared plus y squared minus 2x times y in z. You must know that because we have done the curl topic in previous session. This is my first term, which you can say f sub 1, and this is f sub 2, which is the second term. For the third term I put 0 because there is no k term. Why there is no k term? Because the rectangular area is located in xy plane, not in z. So we only deal with the xy plane, not with the z. So I simply put 0 for the z here. Finally, I got curl f equals to minus 4yk. ds is actually equals to dx times dy, or magnitude of dot product unit vector n and k. Why I use dx times dy? Because the rectangular area is in xy plane. Therefore, I use dx and dy. Substitute the value of the curl, which is minus 4yk, times k. I just substituted the value of curl, which is minus 4y times k. And I substituted k for the unit normal vector y. Let me take xyz plane. Since the rectangular area is located in xy plane, perpendicular to xy plane, there is a z plane where the unit vector of z is k. Therefore, I put k here for unit vector. So k times k equals to 1, and similarly k times k equals to 1 here. My new equation is minus 4y dx dy, where the limits range from x equals to minus a to x equals to plus a. This is along x-axis. Along y-axis, limits range from y equals to 0 to y equals to b. Simply put the limits for the double integration. First integrate minus 4y with respect to x to have yx. I just took minus 4 out of the integration. Substitute the values of the limits, which is minus a and a, to have 2ay dy. Let me take constant 2a out of the integration to have minus 8a integral of y dy. Now I'm going to integrate it with respect to y to have y squared over 2. Substitute the limits here, which is 0 and b. So this is the final value for the right side, which is minus 4ab squared. And it's exactly the same value as I calculated for the line integration at the left side. Remember. So I can see that left side, which is minus 4a times b squared, equals to the right side, which is also minus 4a times b squared. So therefore I can say that Stoke's theorem has been verified.